Hello. So let's get into some more examples with the limits, the numerical and graphical viewpoints. A little bit of highlights. These worksheets are available for each section. I don't know if I have them on Blackboard yet, but if you want them, let me know. Let's remind ourselves what a limit is. Let f be a function such that f of x is defined for values of x arbitrarily close to, but different from a. Then if f of x approaches the number L as x approaches but is not equal to a, regardless from which side, then we say that f of x approaches L as x approaches a, or that the limit of f of x as x approaches a is L, and we write the limit form. If the limit fails to exist or fails to approach a single number, then the limit does not exist. We have two-sided limits, right? We have a limit from the left and a limit from the right. And if the limit from the left is equal to the limit from the right, then the limit does exist. So what I want to talk to you about is some more examples. The examples in my first lecture, there weren't enough of them. So let's take a look at this. Let's see if I can do it here. Here's our limit that we want to find. The limit as x approaches 1 of x squared minus 1 over x minus 1. And it says to do this numerically. So let's look at this numerically. I'm going to pull up Desmos. So here's my function. Y equals x squared minus 1 over x minus 1, right? But I want a table of values, right? Numerically means I'm going to use a table. Now, I'm going to take out this function entirely. Here's what I'm going to do. I'm going to copy, Control C. I'm going to pop a Control V in here. But you see how this has x1? I'm going to just type the number 1, and it's going to become a subscript on my x's. Now, as we get close to 1, from the left or from the right, see, it says at 1 we're undefined, but if we get really, really close, it looks like from the left, the numbers are going to 1. From the right, the values are going to 1. I actually have them plotted here. Yeah, 0.9 is way far away. 1.01. So I'm getting closer and closer. I'm looking at all the values that are super close to 1 but are not 1 themselves. Where am I? There we go. I can conclude that whether it's from the left or it's from the right, these numbers get closer and closer to 2. So I'm going to find my pencil, and I'm going to say that this is equal to 2. X minus 3 over x minus 1. So x minus 3 over x minus 1. I'm going to divide x minus 3 divided by, I was afraid of that. So I'm going to put in parentheses. Again, I'm going to get that out of here because I don't need it, but I'm going to type table. You could also click the plus and get a table. I'm going to highlight, copy. I'm going to delete and paste. I'm going to turn these x's into x1s. And I'm actually going to turn this off. I don't care if it plots for me. I want to get close to 0, so we'll do some negative numbers. Maybe I'll put a negative in front of that. Negative 0.1, right? Maybe a negative 0.001. Negative point, let's put 3 zeros in. All right, we're getting close to 3 as we go to 0 from the left. Where's my graph here? Getting close to 0. I know how to read a graph. There we go. All right, getting closer and closer to 0. It looks like it's 3 from the graph, but if I try to put in 3, where are we? There we are. If I try to put in 0, I'm sorry, as we get closer and closer to 0, oh look, it's just 3. It is getting closer and closer to 3 on both sides. But this is one that we could just substitute in and find the value. So if we could just substitute and find our 3, why not do that? A little harder, right? Now this time we have 6x squared. I'm going to hopefully be able to see it here. I'm going to do a new problem, 6x squared plus 5x plus 100. That's in the numerator. Divide it all by, and I don't use parentheses for the denominator because my fraction's already there. So it's already showing me that that whole thing is going to be in the denominator. I'm going to copy that. I'm going to add a table. Let's delete that. Paste it in, and every place we see an X, put a 1. It automatically subscripts it for you, which is the coolest ever. I want this to be out a little wider. There we go. Now, what are we approaching? We're approaching infinity. All right, 1, 10, 100, 1,000. As we get more and more zeros, notice how closer and closer this number gets to 2. So I feel fairly confident that this will equal 2. All right. So numerically, we could do this one as well. If we put this one in, okay, we're going to put this one in. I'm going to show you all of them, what it might look like on your tables as you do them as well. All right, so last one I'm going to type in, I hope, 10x squared. It's not, actually, plus 1 divided by 5x plus 2, and I decided to use parentheses here. We'll delete that. Take this one. Remember to put in our 1s because that's what our input form takes. Again, we're going to infinity, so I'm going to leave these values. I don't like that 2 to the 7th. Let's see if we can make it decent here. What is that? That's 199,999.2. What do we have? We have a weird number. Okay, then 19, 199, 1999, 199, 999. Notice how, as I add zeros, I'm just getting a whole bunch of numbers, but this is 2 times 10 to the 7th. That's a 2 with 7 zeros after it. 8 zeros after it, 9 zeros after it. What's happening? As the X input gets big, the Y value also gets really huge. Right now, we say this does not exist. But later, we're going to say it has an infinite limit. At infinity. All right, so infinite limit. Right now, it does not exist because it's not a number. Okay, so in the following exercises, use the graph to compute the quantities asked for. Notice it has our scale right here, so every mark is worth 1. The first thing, okay, and here's our function. We're going to assume this is our function f of x given to us. Limit as x approaches 1 of f of x. Here's 1. So my x values are coming in from the left, and my x values are coming in from the right. As I follow this around from the left, I get a value of -1. And as I follow this graph around from the right, as my x values get closer to 1, my y values get closer to -1. Let's mix it up here. Maybe I just need to be patient. All right, so now as I approach -1, right, here's -1. From the left, as my x values get closer and closer to -1, my y values get closer and closer to 2. As my x values get closer to -1 from the right, My y values get closer and closer to 2, so we say this limit is equal to 2. What y value does the graph get close to when x is given to us? Okay, so I'm writing these over on the side. The limit as x approaches 3 of f of x. This is 3, right? 1, 2, 3. As we get close to 3, it looks like the graph gets close to 1. All right, we're just going to cruise down here. Number 2. The limit as x approaches 1 from the right of f of x. 1, only from the right. Remember, we have 0, and what's on the right is positive, positive, and what's on the left is negative. All right, so on the right side of 1, I'm only looking here, so I follow my graph down, and it looks like the y values are getting close to -1. Let's do an orange. Orange is for 3. The limit as x approaches 1 from the negative side. All right, so from the negative side, negative numbers are on the left, so now I am coming in and I'm on the graph approaching 1 from the left, and I still get an answer of -1. So this tells us, let's go with blue, 2 and 3 tell us that the limit for 4 as x approaches 1 of f of x, the limit from the right is equal to the limit from the left, and so the limit is equal to -1. And number 4. But check this out. Let's go a little off scope here. Number 5. F of 1. When I put the value of x equals 1 in, notice that's an open hole. X equals 1 happens right here. It's equal to 1. And our last one, let's go forest green or something like that. The limit as x approaches infinity of f of x. Now this is negative infinity, right? And this is positive infinity. That we frequently don't write a positive, but sometimes you'll see it. If I were to imagine this graph increasing, keep on going forever in the position that it's indicated, it looks like this does not exist, because it goes to infinity. Again, this is another infinite limit at infinity. All right, I'm going to cut it back to just 2 colors for this next one. Last example. Will I? I don't know. Let's see. So I'm just going to put 1. Limit as x approaches 0 from the left. Here's 0. Coming from the left on the graph, it looks like I go to infinity, or does not exist, depending on what your homework indicates. Number 2, as I approach 1 from the 0, what? I have got to read 1 from the right. Here's 1, approaching 1 from the right, that's coming up here, and that has a limit of 0. Number 3, as x approaches 0, as I get super close to 0, this limit does not exist. It does not exist because it does not settle on a specific number. We might say it's equal to infinity instead. If it tells you if the limit does not exist, state DNE, then write the DNE. Limit as x approaches 1. As x approaches 1 from either side, from both the right and from the left, the y values both approach 0. However, let's mix it up a little bit. Number 5, f of 0 is undefined. Oh, that's not true. F of 0 is equal to 0, right? This is f of 0. And f of 1 is equal to 1. So just because a limit exists, right, the limit as x approaches 1 is 0, doesn't necessarily mean the function is defined the same there. A limit just looks at what's going on around it. It doesn't care what's happening actually at 1. It wants to know what's going on near 1 when x values are near 1, or when x values are near 0. All right, more examples to help you out with 10.1. Thanks for watching.